So you have this apparatus shown in the figure with two blocks of mass 1 and mass 2 connected by a string of negligible mass over a massless pulley that turns without friction. So all that stuff just means that the tension is the same throughout the entire string. And block 1 is situated on a frictionless ramp that's inclined at a 30-degree angle. So let's go ahead and draw the free body diagrams for the two blocks. So, as always, they have the gravitational force, but because the two blocks have different masses, or we're going to assume they have different masses, we're going to have to label them as Fg1 and Fg2. Now let's do the tension force. So for the hanging block, it has an upward tension, Ft, and for the block on the incline, it has a tension directed along the direction of the string. And remember, those two tensions are the same because of the massless frictionless pulley. So we don't need to label them Ft1 and Ft2. But then also the block on the incline, because it's on a surface, has a normal force on it. So we need to do an Fn for this block. Remember, it said the incline is frictionless, so we're not going to include a frictional force. Alright, part B. Which block must have a greater mass in order to keep the system in equilibrium? Now, if you remember back to the definition of equilibrium, equilibrium means that the blocks are either not moving or moving at a constant velocity. In other words, they don't have acceleration. So if you think about this in terms of Newton's laws, for a system that has no acceleration, that's implying that is going to be Newton's first law. So we're going to write Newton's first law for block 1 and for block 2. So for block 1, let's rotate the axes so we can resolve some of these things into some components. So let's take this and draw another free body diagram. And on this free body diagram, we're going to have the Fn still directed that way. The Ft will still be directed up that way, but now the Fg1, part of it will go along this axis across from the Fn, and that should be an Fn up there. So that's going to be Fg1 cosine theta, and then part of the gravitational force will be directed this way, and that's going to be the Fg1 sine theta. So for block 1, the net force in the x direction equals 0, Newton's first law. The x direction is going to be the direction of motion. The y direction would be this way with the normal forces. So because it is Newton's first law, we are just going to say that the leftward forces equal the rightward forces. Or the rightward force of Ft is equal to the leftward force of Fg1 cosine theta. And I'll go ahead and replace that Fg1 with mass 1 times g. So Ft, the force on the right side, is equal to m1g times sine of theta. And we'll do the same thing for block 2. We'll do the net force. This time for block 2, we're going to do the y direction. Notice on block 1, we did not need to do anything with the y direction yet. You normally only deal with the y direction for an object on a surface when there's friction involved, because friction, if there was friction down here as well in this direction, when you plug in the formula for friction, it has a normal force in it. So to figure out what that normal force is, then we have to do the y direction, because that will typically tell you the normal force is equal to, in this case, Fg1 cosine theta. So for block 1, we only had to do this x direction. Now in block 2, we are only doing the y direction because there's nothing in the x direction. And because it's an equilibrium, I'm just going to set up equals down. So, and if you want to illustrate this on the diagrams, just to be really clear, you can put the little tick marks on this diagram, like right here and right here, to illustrate that they should be the same length. You can't do that on the original diagram for this one, but you can do it on the redrawn diagram, because you know in the redrawn diagram that this will be equal to this, and I'm doing a double tick mark here because I've already used the single tick marks over here. And then also, you can say that this, with 3 tick marks, is equal to this. It's not necessary, but it doesn't really hurt to do it, so that's why I did it. So, back to block 2, as I keep going off on tangents. Up equals down. That's going to be Ft is equal to the gravitational force, Fg2, which we can just replace that with mass 2 times g. So, those are our 2 equations. And notice that we have 2 equations both for Ft, and we also know that this Ft is equal to this Ft. We said earlier that the Ft's were equal. So, since both of these equations are for Ft, why don't we just set them equal to each other? So, for that, we have m1g sine of theta is equal to m2g. Notice that we have a g on both sides of the equation, so we can cancel that out. So we have m1 sine theta is equal to m2, and just by looking at this equation, since theta is equal to 30, we know that this part right here, the sine of theta, has to be a number less than 1. In this case, sine of 30 is equal to 0.5, so what it's saying is m1 times 0.5 is equal to m2, which means that m1 has to be bigger than m2 because you're basically cutting it in half to equal m2. And you could have figured this out even if you weren't given the angle, just based on the fact that sine of theta has to be a number less than 1. So it's going to be m1 times a number less than 1 is equal to m2, so block 1 has to be bigger. So this one is easiest to justify it mathematically just by writing it out like this. And the equation we just wrote also helps with part C, determine the ratio of the masses m1 over m2 that would keep the system in equilibrium. We've already done most of the work now, because if we just take this equation and just rearrange it to get m1 over m2, so divide both sides of the equation by m2, so we have m1 over m2 times 0.5 equals, and this side would just become 1. Then just divide both sides by 0.5. So m1 over m2 is equal to 1 divided by 0.5, which is equal to 2. So that tells you that mass 1 over mass 2 is equal to 2, or you can say that mass 1 just has to be twice the mass of mass 2. So that, the simple number 2, is the answer to part C. And part D, now suppose the ramp is not frictionless. So if the ratio of masses is slightly higher than determined by this number right here, so let's say it's like, I don't know, 2.1, would the frictional force on block 1 be directed up or down the ramp in order to keep the system in equilibrium? So if the ramp were still frictionless, increasing this ratio, meaning F1 would be a little bit bigger than, or M1 is now a little bit bigger, or M2 is now a little bit smaller than what it currently is, that means that because M1 is bigger than M2, it's going to cause M1 to want to go down the ramp, and M2, the hanging mass, to move upward. So if M1 wants to now go down the ramp, to cancel that out, with the ramp being frictionless, the friction has to be in the opposite direction of the motion. So with M1 wanting to slide down the ramp in this direction, the frictional force has to oppose that. So there's going to be a static frictional force directed up the ramp.